Hello, today topic is boundary condition for D vector, B vector, E vector and H vector are interface between different media. Consider two media. This is medium 1 and right side that is medium 2. Its permittivity is epsilon 1, permeability is mu1 and epsilon 2 and mu 2 are that of medium 2. And this the boundary. So boundary may be a line or a surface. It separates these two media. So when a field vector passes from one medium to another, its magnitude as well as direction may change. So how much the magnitude of the field vector changes. So this is the field vector. Suppose this field vector is E1 and E1 changes to E2. Similarly for other field vector D, B and H. Generally, the field vectors D, B, E and H will be discontinuous at this boundary. When it crosses across this boundary, they will be discontinuous. So the nature of this discontinuous can be deduced using Maxwell's integral form. So let us first discuss boundary condition for D vector. So this is a surface that separates two medium 1. The region above this surface is medium 1 and the region below this surface is medium 2. So this is a Gaussian pillbox, very thin and small in size. Electric displacement vector D on the upper region is that is D1 and on the lower region is that is D2. So these two field vectors are different. In medium 1 that is D1, in medium 2 that is D2. We take a unit normal vector here. So this is n1 cap and opposite to it on the bottom surface the unit vector is that is n2 cap. To find the boundary condition for D, we apply the integral form of Maxwell's equation, that is Gauss law. Integral form of Gauss law is that is D dot dA is equal to Q ENC, charge enclosed. It can be written as surface integral D vector dot area vector is that is n cap dA. N cap is a unit vector normal to the surface area. So this is equal to Q ENC. So let us apply the surface integral on this pillbox. So on the top surface, suppose S1 is the top surface and S2 is the bottom surface. So it can be written as surface integral over S1 D1, here electric displacement D1 dot unit vector is n1 cap dA. Then on the bottom surface that is plus surface integral S2, electric displacement is here D2 dot n2 cap dA. Then surface integral on the walls that is plus contribution from walls, that is equal to the charge enclosed by this surface. So volume density we know rho f. So charge enclosed, that is equal to volume integral of rho f d tau. Rho f is the free charge density. The wafer is very thin. When the thickness of this wafer tends to 0, the volume of the Gaussian pillbox that becomes tends to 0. So in this limit, the volume density of free charges contribute nothing, but only the surface contributes the charge. So QNC, that is equal to surface integral of sigma f dA. So this is surface integral, and this becomes, that is sigma f A. A is the area caught by this Gaussian blocks on this boundary. So area of top surface is A, area of bottom surface is A, and where it caught the boundary, the surface area is A. So that surface encloses this charge sigma f into A. So this is sigma f into A. In the limit, when the thickness of this wafer tends to 0, the contribution from this wall, the surface integral of D from this wall, that becomes 0. So we can write this is d1 dot n1 cap A plus d2 dot n2 cap A, and contribution from walls is 0. This is equal to sigma f A, or d1 dot n1 cap plus d2 dot n2 cap is equal to sigma f, after being cancelling A from both sides. Now n1 cap is equal to minus n2 cap. Suppose this is equal to n cap. So we can write d1 dot n cap minus d2 dot n cap is equal to sigma f. So d1 dot n cap means this is the normal component of D, that is d1 perpendicular minus d2 perpendicular, normal component of D, that is equal to sigma f. So the component of D vector, which is perpendicular to the interface, is discontinuous in the amount, that is sigma f. Same identical regime is applied to find the boundary condition for B vector. The integral form of Maxwell's equation for B is V dot dA is equal to 0. We apply the same identical regime to find the boundary condition for B. So if you write in detail, then we can write surface integral B dot n cap dA equal to 0. We draw the same a teeny wafer thin Gaussian pillbox which has top surface S1, bottom surface S2, and walls. So surface integral for top surface is, that is integral over S1 B1 dot n1 cap dA, plus on the bottom surface integral is S2 B2 dot n2 cap dA, plus contribution from walls that is equal to 0. The edge of the wafer is very thin, so the last term vanishes because the flux from these walls is 0 as thickness tends to 0. So we can write B1 dot n1 cap into A, surface integral of dA is, that is A, this area is A, plus B2 dot n2 cap A is equal to 0. Area of top surface is A, area of bottom surface is also A. Or we can write B1 dot n1 cap plus B2 dot n2 cap is equal to 0. Since n1 cap is equal to minus n2 cap is equal to n cap, so we have B1 dot n cap, and this is minus B2 dot n cap is equal to 0. So B1 dot n cap means this is the normal component. Suppose this is your B vector, this is B1 vector, and this is N1 cap. So normal component of B1 vector along N1 cap is, that is B perpendicular. So this is B1 perpendicular minus B2 perpendicular, that is equal to 0, or B1 perpendicular minus or equal to B1 perpendicular is equal to B2 perpendicular. Thus, the normal component of magnetic induction is continuous across the boundary.